Hi, Intro to Calc. Hope you guys are having a great day. We are moving on to Chapter 1, Section 8, Day 1 of Calculus, a Single Variable. And we're going to introduce the concept of limits today. So, long story short, a limit is basically a value that a function approaches. Yeah, that's about it. And like more formally, it's written as the limit, LIM for short, as x approaches some number c of a function f of x equals a number. So I'm going to write that out for you. Okay, I think it makes more sense if you can see it. So we write the limit as x approaches c of f of x equals L if the values of f of x get close to L as x gets close to c. Okay, so what does this look like actually on a graph, and what does that actually mean? Basically, all it means is that, for example, if I wanted to know on this graph what's the limit as x approaches, let's say 0, because that's where the funky point is, of this function. So f of x, they described it as f of theta, but same idea, right? So we're looking at the limit as x approaches 0 of sine of x over x. So the idea is you're looking on the x-axis, so we're just kind of like, as x approaches from either side, from the negative side or the positive side, 0, which is right there in the middle. So as x approaches that number, then the limit as x approaches that number of the function is what the y value is approaching at that point. So at that point, it looks like the function is approaching 1, right? The y value is, it looks like as x gets closer to 0, y gets closer to 1, basically, is what that graph means. And that's essentially what a limit is, in long story short, right? As x approaches 0, y is approaching 1. So from the last video, we talked about continuity, and that basically a function is continuous if you can draw it without having to lift up your pen. But specifically, continuity at a point, you need, for the formal definition, you need to know what a limit is. And so the idea is, for functions, if I want to know whether or not this function is continuous at, say, for example, that point, then the limit as x approaches 0, or as your independent variable approaches 0, and your y approaches 1, your limit, in this case, we'll go back to theta, the limit as theta approaches 0 of sine of theta over theta is 1, right? Because that's kind of what we just talked about. But that's not equal to the function evaluated at that point. So sine theta over theta at theta equals 0, right? So remember, we're approaching 0, but when we actually equal 0, there's a problem, right? Because sine of theta is 0, sine of 0, divided by 0. And the problem is you can't divide by 0. Bad things happen when you divide by 0. Things blow up. You can't divide by 0. So you have essentially 0 divided by 0. That's a problem. You can even ask Siri what 0 divided by 0 is. And Siri knows that it's a bad thing. So anyways, so the idea is, if your limit equals the value at that point, then the function is continuous at that point. But if it does not, like in this case, then it's not continuous, which makes sense because I can draw this thing, but I have to pick up my pen at x equals 0 and y equals 1, okay? So that's kind of the formal definition of a limit. Okay, so there's your formal definition. A function f of x is continuous at x equals c if the limit as x approaches c is actually equal to the function at c. Okay, cool. So then we want to talk a little bit about a more formal definition of limit. So we're going to be this is just like a fancier way to write it, right? We can define the limit of a function f of x as x approaches c, written as this thing, to be a number L, such that f of x is as close to L as desired whenever x is sufficiently close to c, but x does not equal c, blah, blah, blah. Okay, that's like a long definition. It's kind of confusing. But basically, all it's saying is that the limit as x approaches c is equal to L if whenever I get closer to the x value, so whenever I get closer to c, I can also get closer to the y value as well. And the closer and closer I get to the x value, the closer and closer and closer I get to the y value. Okay, now here's the doozy. This is the official formal definition of a limit. This is probably more confusing to understand. Probably, definitely. A lot of people struggle with this definition, but it is important. Sorry, I have the hiccups. It is important to at least understand the basic concept before moving on from limits. So this is kind of how the formal definition goes, right? So we define the limit as x approaches c of f of x. Okay, so same thing as we did earlier. To be the number L. So again, we're still kind of we're just talking about this right now and giving it a formal definition, such that for every, that's a Greek letter, it's called epsilon, epsilon greater than 0. Oh no. Okay, there it is. So for every epsilon greater than 0, so basically epsilon represents a small number, and it can be as small as you want it to be. So like if I say an epsilon of 0.1, you could repeat this process for an epsilon of 0.01 or 0.0001, something really, really small, but is still larger than 0. It's got to be a positive number because it represents like a distance. So we define the limit as x approaches c of f of x to be the number L, such that for every epsilon greater than 0, there exists a delta, and also another small number, greater than 0. Okay, so delta kind of looks like a weird curly hook D type of thing. Again, it's just representing the small number that's larger than 0, such that if the distance, so remember absolute value is the distance, so the distance between x and c is less than delta, so smaller than this small number, and x doesn't actually equal c yet, then we can say that the difference between the function and the limit is less than our small number epsilon, whatever it may be. All right, so basically what this means is that if I'm interested in like what's happening at x equals 1, okay, so that's going to be our c value on this graph. I'm interested in knowing what happens on the function there, so that's our limit. So this is L, right, our limit, and this is c, the value that x is getting close to, and this is the value that y is getting close to. So the idea is if I give you an epsilon, like a small distance, so let's say, for example, I don't know, like 0.1 away from L. This distance here, that value would be L plus that 0.1, or L plus epsilon. And then this spot down here would be L minus epsilon. Okay? And the idea is if I give you a value like 0.1 for epsilon, then you should be able to give me a delta on the x-axis that actually gets me even closer to L than epsilon does. So I've changed a couple colors here, but basically this range is epsilon away on both sides, absolute value, of the limit, L, which is what I'm trying to get close to. And so what I need to do is I need to find, or your job, if I give you that epsilon, it's your job to find me a delta on the x-axis that actually gets me closer to L. So that delta would be like somewhere like here and here. Because what that would do is it would actually close the gap, and I would be allowed to get closer to the limit than I did with epsilon. So these two dotted lines to the left and the right of C would be C minus the delta that you give me and C plus the delta that you give me. So basically it's kind of like a game where I give you a small number and you try to find a smaller number. And basically if we can close that gap and get closer and closer and closer, infinitely closer to L, then that limit exists at L. It doesn't necessarily mean that the function equals the point there, but that's not what we're looking at. We're looking at as we get closer and 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 closer, you're approaching a limit. Okay, so as an example for the epsilon delta definition, say we have the limit as x approaches 3 of 2x, and we want to prove that it equals 6. So basically we're looking at if f of x is less than L, if f of x minus L is less than epsilon, then I need a delta so that x minus c is less than that delta. So in this particular case, f of x is just 2x, and the limit L is 6. So I'm going to rewrite this part for this particular example. So I have the absolute value of 2x minus 6 is less than epsilon. Okay, now I also need to find a delta so that x minus c, which in this case is 3, I have x minus 3 is less than delta. So I need to find a delta so that whatever I give you as epsilon, you can find me something smaller. So what you can do is kind of manipulate this 2x minus 6. If I pull out a 2, I have x minus 3 left, less than epsilon. And then I divide both sides by 2, and I get the absolute value of x minus 3 is less than epsilon over 2. And so basically, if you notice, I have the same setup as over here with delta. So basically the idea is if delta is less than epsilon over 2, I can sufficiently prove, like if you give me 0.1 as epsilon, then I can give you a delta of 0.1 divided by 2, or 0.05, that gives me a smaller value of epsilon and is getting us closer and closer to that limit. Okay, so here are the solutions for the rest of them. If you haven't tried these yet, pause and give them a try before you check. But here's your formal definition of the limit. This is kind of what the graph of sine 2 theta over theta looks like, and it looks like it's approaching 2 on the y-axis here. And then for 4, you can either graph it and look at what's happening at 2, or you can kind of plug it in and it works out pretty nicely there. So There you go.